Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hello everybody. Welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host as always. Welcome to our podcast. We also like to thank all the listeners that listen on iTunes, Spotify, Spreaker, iHeartRadio, all these others that carry our podcasts. We'd like to thank you for your dedication and your support. Also, those that listen to what we call the simulcast, which is what we share on the YouTube channel, which doesn't get the major part of our traffic. Our podcasts are really through the syndication, through the other outlets, but we do like to share them on our YouTube channel along with our videos. That way it gives you one more option to be able to go listen to. But we understand that that's a little harder platform to listen when you're out in the field, and we know that you like to listen from our website. We get the most listeners from our actual website, believe it or not. We track the analytics, so we know when you actually click on the listen button on our website, which is masterthenec.com, that's where we get the most listeners, believe it or not. Okay. Anyway, today's episode is a continuation on the one-family dwelling calculations. We previously did a podcast, and it was dealing with the standard method, which is the general method to use, especially on exams, unless they state to use an optional method. It's the standard method. We walked you through that. It was pretty simple, staged process. You just simply followed the process down. We showed you how to use all the calculations and do everything to solve that. And when we did a neutral, we showed you that you had to use the standard method to size a neutral conductor or the grounded conductor for both the optional or standard method. But since we did the standard, it's now time to do an optional method. And we're going to use all the same values that we used during the standard method in order to do this optional method. Now, it's a one-family dwelling. We have the same parameters that we're going to talk about in today's episode. And today, the optional method goes a lot quicker than the standard method. And I'm going to hope at this point that you did listen to the standard method calculated load presentation podcast that we did previously. That way, this one will be slightly better for you to understand because you know where these values are coming from. And so it's a little easier for you to get. So hopefully you've done that. If not, stop right now, listen to this one later, go back and listen to the standard method one we have as well, and then you can come back and listen to this one, and you'll be able to get a better understanding of what we're talking about. All right, so today we're going to talk optional method, one family dwelling, but again, remember this could also apply to the individual dwelling unit of a multifamily building. If you need to solve what the actual load is going to be for that dwelling unit so that you can size the feeder to that dwelling unit, then this is what you do for that individual unit. That's how you get all the usable values here, that when you end up having to do something like a multifamily calculation where you might have 6 or 12 or 20 units, then you need all these values to be able to use that to solve your multifamily. So if you know how to do the standard or optional, then it makes it easier for you to do the multifamily calculation, whether you're using the standard method or an optional method, either one, okay? So we really have to start with the foundation. And the foundation is understanding how do we do the dwelling units or one-family dwellings or each individual unit of a two-family dwelling, how we come up with these loads. And that's what we're doing here as part of this podcast series. All right, so today, optional. So let's do some givens. First thing we want to remember is that we have a single-family dwelling, and it was 2,500 square feet. It's the outside dimensions. Again, we're not including anything like open porches, garages, unused or unfinished spaces, not adaptable for future use. In other words, it's like an attic that doesn't have a high enough ceiling, or the joists or floor joists are not adequate enough to support any load, so you really couldn't use it for anything. So then that is really not adaptable for future use. So you don't have to consider that square footage. A basement, if it's unfinished, it sure is adaptable for future use, so you would have to count that square footage. All those goodies still are in play. All right, so in our example, we're trying to find the general lighting and receptacle load. Now, if you listen to the presentation under the standard method, you understood that when we say general lighting and receptacle loads, that we really are taking into account all of those general use receptacles, okay? The ones that you would be, spread around your room and things like that. Obviously, we have to take into account small appliance branch circuits and laundry branch circuits, but when we're talking about those general use branch circuits, the general use receptacles, that general lighting, then all of those would fall underneath the allowance here for the general lighting and receptacle loads. Now, what's different with the optional method is that we're not going to be under 220.12. We're going to be under 220.82B1. And the reason we're going to be under that is because we're dealing in Part 4, the optional method. Now, in an exam, you might be required to use the standard method. But if it ever tells you to consider the optional, then you need to know how to use it. The other reason that you need to know how to use the standard anyway is because, again, when you're doing the grounded conductor or neutral calculation for a specific unit, dwelling unit or single-family dwelling, you can't use an optional method for that. Okay? You're going to have to use the standard method. So you have to be able to figure out how to do this application. But there is no optional method for calculating a neutral conductor. Okay? So you have to understand how to do both standard and optional. So you cannot make it through your life doing the optional method in order to be able to also size a grounded conductor, because you're going to have to know how to do the standard to be able to do that. So what better way is to learn to do both of them, right? That's what we're here for. So let's do the optional today. So I'm going to give you some of the givens that came from our previous podcast. So first things first, if we look at 220.82, you'll see that we're talking about feeder and service loads. In our case, we're talking about service load today. And it says this section applies to a dwelling unit having the total connected load served by a single 122/40 volt or a 208Y120 set of 3-wire service or feeder conductors with an ampacity of 100 amperes or greater. Okay? So, it could be a 122/40 volt single, or it can be a 208Y120 single. Okay? It's derived from a 3-phase, but it is single-phase application here. Set of 3-wire service or feeder conductors with an ampacity of 100 or greater. So we're dealing 100 and greater. All right? So we know we're there. We are in the realm of being able to utilize 220.82. Now it goes on to say, it shall be permissible to calculate the feeder or service load in accordance with this section. And when we say this section, we're talking about 220.82. This is the section. Instead of the method specified in Part 3 of this article. Means that I'm allowed to use this optional method rather than the standard method, which is Part 3. Okay? Now, the calculated load shall be the result of adding the loads from 220.82B and C. So you add them together. It says feeder and service entrance conductors whose calculated load is determined by this optional calculation shall be permitted to have the neutral load determined by 220.61. Okay? All right, so in this case, that's just basically telling you we're going to size the neutral, and ultimately you're still sizing the neutral using the standard method. Okay? Because there is no optional method for neutral conductor sizing. Okay? And then we'll talk neutral again. I gave you a little insight to that when we did the standard method, but I'll show you some things also when we're doing the optional method that'll help you out. Okay? And again, with the optional method with the neutral, again, maybe I won't re-go over how I did because, again, remember, it's the same as doing the standard method. Nothing different. So you still have to know how to do the standard method. Okay? All right, so let's get into it. So number one, we're dealing with 220.82B1. Okay, and that's going to give us the general. Now, there's two pieces, B and C here, and that's all we're going to use here is B and C to solve these equations, okay? All right. So, general loads, it says, now we're under, again, for you that are following along, we're on page 78 of the PDF, or we're on page 75 of the hardbound edition. It says, the general calculated load shall not be less than 100% of the first 10,000 kVA, plus 40% of the remainder of the following loads. Okay? And then we're dealing with item 1, item 2, item 3, and item 4. So these are the loads we're considering at this first stage of the game. All right, so number 1 says, you know what? Unlike the standard method where I had to go to 220.12 and I ended up going to the table, since we know that we're doing dwelling units, because that's what the header is, or the charging statement under 220.82 is, dwelling units, then immediately it tells us to use 3 VA per square foot for the general lighting and receptacle use. Okay? We got that. It also reminds us, again, use the outside dimensions for our square footage, and we did that with the standard method, so nothing else changes. Again, hopefully you listen to the standard method before you listen to the optional method so that I don't have to rehash all this over again. The next one, it says, don't include open porches, garages, unused, or unfinished spaces that are not adaptable for future use. Okay, an attic, for example, that doesn't have headroom, or the floor joists are too small, or in this case, I guess it would be the ceiling rafters for the room below it. Whatever it is, if they're too small, they can't support storage weight, then it really isn't adaptable for future use, and I don't have to consider that square footage. Okay, but if I had an unfinished basement, it is adaptable for future use, then I have to count that square footage because I could finish it off, and it doesn't necessarily mean I'm going to put a new service in, right? So I've got to account for that expansion. All right. So that's the first one. The next one says, you know what? Those small appliance branch circuits and that laundry circuit, you're going to account for those as well, just like we did in the standard method. So in our case, there was a minimum of 2 small appliances and there was a minimum of 1 laundry circuit. So you're going to have to account for those applications, okay? So that's what we've got here. All right, so in our case, let's kind of work through this because it's a little different. So as we're working through this, I'm going to work it together so you see how easy this is. And it's almost put down logically on paper in the code. They did a great job. So first thing is at 3VA. Well, we knew that it was 2,500 square feet. So we do 3 times 2,500. That's 7,500. Again, the same way we did this for the standard method. We write that down. The next, we knew there was a minimum of 2 small appliance branch circuits. That's where the B2 here comes into play. So it's 1,500 times 2. That is 3,000. Now remember, if you have more than 2, you got to account for the more than 2. But in this case, we only had the minimum of 2. Next is the laundry branch circuit. We only did the 1, so it's 1,500 times 1. So that is 1,500. So you add the 3 together. Okay, when you add those 3 together, that came out to 22,328. Now, we didn't do anything with 220.42. We don't have to do the 35%, 25%, subtract the first 3,000. We're not doing that. That was the standard method. We're doing the optional method, baby. We're just adding things up, okay? So, 2,203.28. Write that down as a temporary value for right now, okay? Next, let's go on to the next thing. What's the next thing? Well, the next thing is the appliances. Now, in the appliances, it's pretty darn simple. We take the nameplate value, and that's it. So the water heater was 4,000 kW. Remember, we convert that. It's the same as equal to VA, so it's 4,000 VA. The dishwasher was 1,500 VA. The clothes dryer was 4,000 VA. Now, why don't we not take 5,000 for this? Because in the standard method, it was 5,000 or nameplate, whichever is greater. In the optional method, we're strictly pulling the nameplate. That's why it's a much easier calculation. So we take the 4,000, and that's what we put down. The disposer, we still had to do that conversion because it was a 3rd horsepower at 115 volts. We go to 430.248. We find what the actual 7.2 amps was times 115 volts. That gave us 828 as the VA. Well, that's what we write down. The 828, that's the VA. Remember, we've got to convert those horsepowers into VA. The next was the range. Remember the range. It was 12 kW. Now, we only used 8 kW because it fell in column C at 220.55 on the standard method. But no, using the optional method, it said clearly take the nameplate. So we literally take the nameplate. So we took the nameplate rating of 12,000. Now, what did we just do? We took the water heater, the dishwasher, the clothes dryer, the disposer, and the range at nameplate value. If you look at the code and you look under 220.82b, 1, 2, 3, and 4, that's just what we did right there. All we did was take the VA per square foot. We accommodated for the small appliance and laundry. We took the nameplate rating of all of the appliances. We took the nameplate rating of the range. We took it of the dryer, and we took it of the water heater. That's it. We took those values. Now, what do? Okay, Well, the next step would take those values for the appliances and we add them to the values that we calculated before of the 7,500, the 3,000, and the 1,500. What do we get? We get 22,329. Okay? That's our total. Okay? For those appliances right there. All right? Now, let's double check and make sure that is the value that we've got. Actually, you know what? That wasn't. That 22,328, that's just all of our appliances. So, okay. So, you have to take the first value. That was the 7,500, the 3,000, and the 1,500. And then you keep that. And then you add up all your appliances, and that's 22,328. Now you add up all four of those. So we add up the general lighting receptacle loads, which is 7,500. We add up the two small appliances, with 3,000. We add up the laundry, which is 1,500. And we add up all of the appliances. You just add them all together, and that was 22,328. Add all those up together, and we end up with 34,328. So that right now is the total sum of all four of those values that we added up. Okay, now, we're going to finish the first part of B, and that is, what do we do? Okay, all right, and in our case here, it said the first 10,000 at 100% and the remainder at 40. So usually what I like to do is take that 34,328, take 10,000 away from that. Just put it to the side. Just put it over. And what does that give me? 24,328. Now, that is the remainder. Okay, we already put the 10,000 aside. So that remainder we do at 40%, right? So we take that 24,328, you multiply it by 40%, and that results in 9,731. Okay? Now, add that 10,000 back. And now it's 19,731. Okay, guys, write that down. That is your total for the B, the general loads. It's 19,731. Write that down. What's next? Okay, well, let's move down. For the heating and air conditioning load. Now, this is pretty simple. You've got 1, 2, 3, 4, 5, 6 options here. You have the air conditioning and cooling, right? And we had that in our equation. And then you have the heating. And we have to accommodate that. Now, the difference between the standard is it simply takes it as a combination, whereas when you're dealing with the optional, you have to break it out a little bit, okay? So we have our air conditioning and cooling, okay? And it also includes heat pumps without any supplemental electric heat. So if you have a heat pump that doesn't have supplemental electrical heat, or electric heat, I should say, then you're still going to use 100% of that value for that, okay? So that's air conditioning value. So you have the different applications here. Now, that was our AC. And if you go back and look in our AC, I'll just kind of refresh your memory what we were dealing with. All right, so here's where people get confused because you have a number of items here. Now, ours, we were dealing with a heat pump. Now, we had determined early on, even in our standard calculation, that they were non-coincidental loads. Okay, so 220.60, I believe, that said they're not, I don't know if it's 220.60. I should look real quick. I just want to look because I want to be accurate. Yes, 220.60, non-coincident loads. So they are going to be on at the same time. So in our case, our option is to compare the AC at 100%. And remember that when we did the standard method, the AC was larger. Okay, it was larger automatically. So here you notice it says, number 1 says 100% of the nameplate of the air conditioning and cooling. So we already know we're taking that value at 100%. We've already calculated that out. Okay, we knew that was 7,613. But when we're comparing it to the heat, in our case, we're utilizing, if you're in the National Electrical Code, for this example, we're using item number 3. It says 100% of the nameplate rating of the heat pump compressor and 65% of the supplemental heating for the central electric space heating system. Now, if the heat pump compressor prevents from operating at the same time that the supplemental heat is, then I get to omit the heat pump compressor, and I actually will use the supplemental heat, and it still goes to 65%. Okay? So in our case, it was 6,000 kW for the heat, and the application here was the additional air handler, which is the blower motor, which is the 667. That was the 1/4 horsepower at 115 volts, and you know how to do that, right? You go to 430.248. You find the column that deals with 115. You find the 1/4 horsepower, and that equals 667 VA, because you took the value there and you did that and you multiplied it by the voltage, and that's how you come up with the VA. So that was 6,667. Now, if I do that times 65%, then that's going to be obviously less still than 7613. So I could really stop there. I could know that the AC is going to be larger. But if you wanted to work it all the way down, the 6,667 times 65% is 4334. So I'm omitting the heat. I'm going to stick with the AC in this case. But remember, there's a bunch of different options here. Okay, if you have electric space heating, like a baseboard heat, and again you have less than 4 of them, then you do it 65%. If you have 4 or more, then you can do them at 40%. So you do have some values here when you're comparing the AC. But the AC gets considered at 100%, and you get the other. Okay, all right. So that's kind of how we're doing it. And again, there's just a bunch of options here. So we took the AC. So we write that down. So that's our next value is 7,613. So that is the total value for C. Now, what did it say earlier? It said to combine B and C. So it's just that simple. You take the 7,613, okay, and then you take this 19,731, which is the result of our B calculation, and together that's 27,344. Okay? All right, so hopefully you got all that out of you. So that's our total, 27,344. All right, what do we do next? Well, in our case, we know that it was a 27,344, and we know that we're dealing with a 122 40-volt application. So we're going to take the 27,344, we're going to divide that into 240, that's our voltage, and that's going to result in 114 amperes. Okay? Now the reality is the value was 113.9, but again, 0.5 and greater is a major, so you round it up, and that's how we got to 114. Now, what size overcurrent device do we need to protect this, to handle this 114 amperes? Okay, what do we need? So the minimum size service rating that we'd be dealing with is going to be, well, we'd go to 240.6 and see what we're dealing with. So let's do that. So I go to 240.6 and I'm looking for something that's got to be able to cover the 114. Well, 110 is not going to work. So the next size up is 125. So 125, but I have to have a conductor that can at least handle the 114 amperes of the load. Okay, so as I showed you in the other application, in the standard method, one of the things that we would do at this point would say, okay, well, if I don't want to do anything, and I just need to find out what I need to give me 114 amperes, then one thing is people will go, and we're not talking about any adjustment or corrections. None of that have been talking about in this podcast. I would encourage you to go watch or listen to my podcast, or actually my video on derating demystified. It's over on our YouTube channel. You can get there from our website at masterthenec.com. And there you will see how to apply adjustment and corrections, and I go through all of that, so I don't want to rehash that here. We're simply doing loads today. And I'm assuming 75-degree column because we are over 100 amperes, and if you know anything about 110.14c, it's going to tell you that you're going to be in a 75-degree column. So I'm in the 75-degree column based on the ampacities we're working with. And so when I come down here, I need to pick a conductor that's going to give me the ability to handle 114 amperes. Okay, so in this case, it looks like it would be a 2 copper, and that can handle 115 amperes. Okay, is that going to be able to handle the 114 amps? Absolutely. Okay, so that's where we're at right there. Now, one of the things that I want to remind you is because of this service is indeed, okay, and it's not going to make a difference in this calculation, but I want to make you aware of it again, just like we did. If you get an exam that says, give me the minimum size, you need to figure out whether or not it falls under this little thing that allows you to use 310.15b7. Now, I talked about this extensively in my derating demystified video, but I also referred to it in our standard method that hopefully you listen to before you listen to this podcast. And basically what we're saying is, if I'm dealing with a service or feeder that falls between 100 to 400 amperes, and I'm dealing with a application where it is a 122 40 volt application, okay, that's one of the things I'm dealing with. Or if I'm dealing with a application where it's a 208 Y120, and I'm dealing with two ungrounded conductors and a neutral conductor from a 208 Y120 system, then I'm permitted to do something here, and that is to come up with a conductor's minimum size that must be maintained, and that is 83% of the service rating. Okay? So, how do I do that? Now, in this case, for the optional method, it's not going to make a difference, but we need to understand how the math works. So, in this case, what it says is go to 31015B7, and you're going to go down to B1, and it says, for services rated 100 through 400, in this case, it's rated 125, so we fall well within the scope, and it says the service conductor supplying the entire load associated with the one family dwelling. In this case, it's just only 1 meter, hits one panel, serves all the loads. That's all we're doing in this calculation, okay? It says it shall be permitted to have an ampacity not less than 83% of the service rating. Well, our service rating is 125. So, what is 83% of that? And that is the minimum size you must be maintained. So, if you do that and you go 125 times 0.83, that is 103.75. So I have to have a conductor that at least can handle 103.75 amperes. Okay, and that would be the minimum size. Well, if you go look at 31015B16, you're going to notice that previously we said what? That we needed a 2 gauge? Well, the next one smaller is a 3, and that's only good for 100. So we need to have at least 103.75. So that still would put us in the 2 gauge because that one can handle 115. So in this example, it wouldn't matter, okay? Simply wouldn't matter at all right? But it's important that you understand that when you have the ability to use 31015B7, that you can utilize it, okay? So on an exam, if they want to know what the minimum size would be, then that's when you can utilize 31015B7. And again, it's not an exception. It is permitted to use it, okay? So use it. Now, could I be larger than that? Obviously, if I just went to 31015B16, obviously it could be larger. But is it really the minimum size? Absolutely not. It's not necessarily the minimum size. So keep that in mind, all right? All right, so then we move on, and then lastly, like in the other episode, we sized everything. We know the ungrounded conductors are 2 copper. Next was the grounding electrode conductor. If we have ground rods, again, 250.66a says for ground rods, it doesn't need to be larger than a 6 AWG copper or 4 AWG aluminum, although if it goes to a ground rod, it's driven in the earth, then it's probably going to be a termination in less than 18 inches, so you wouldn't use aluminum because of that, but you typically could use copper. So it doesn't need to be smaller than a 6, okay, for that application, generally for the ground rod. However, it doesn't have to be, but here's a neat thing. You have to look at the application for sizing the grounding electrode conductor, because there might be an application, depending on what you're doing, that it could be actually smaller than a 6. And so we're going to use that to give you an example here in this episode and show you this, because we're dealing with a 2 copper. So what I want you to do at this point is go to 250.66 and look at how this works, because I really didn't tell you. An exam might not tell you what exactly the grounding electrode is. And so if it doesn't tell you what it is, then you really can't use the permitted allowances in 250.66A, B, or C. That's for concrete electrode, the ring, or the rod, pipe, or plate, because it didn't tell you which one it was. If it doesn't tell you that, then you're going to have to go to the table 250.66. And whereas a ground rod doesn't have to be larger than 6, well, for the ground rod. However, since I don't give you what it is here, what size is it plausible that it could be? So let's go look at that. So if you take your code book and you go to 250.66 with me, and let's look and see, since I really didn't tell you what it was as the electrode, then that would tell me that I'm going to be firmly and 250.66. And ultimately, if A, B, and C doesn't apply because they don't state otherwise, that's going to throw you down under the table 250.66. Well, if you look down here, remember we said it was a 2-gauge copper? Well, you see 2 and smaller under this table. That is the ungrounded conductor, and that is the largest because it is a 2. Then it doesn't have to be, it can be 6-gauge. Now, because it is 6-gauge, and when you're dealing, 8-gauge, when you're dealing in those that are smaller than 6, then you really do have to protect it against physical damage. So you're probably going to put it in like a Schedule 80 PVC if you want to be less complicated about it, because if you put it in something like EMT, then you're going to have to bond it at both ends, and that gets into all those requirements of bonding around the grounding electrode conductor, and that's for a whole different episode. All I'm saying is it could be an 8-gauge at this stage because we're dealing with a 2-gauge as our ungrounded hot conductors. Okay? Now, only drawing attention away from that is to the 250.66 to let you know that, well, if it is a ground rod, okay, then it says here, it says, shall not be required to be larger than a 6. Okay? To that. All right? It doesn't require it to be larger than a 6. But it most certainly could be smaller than a 6. But then you're going to have to get into that protection. Okay? All right? So basically what it's saying for a rod, it doesn't matter whether it's a 5,000 amp service with multiple sets. If it's a ground rod, it just doesn't have to be larger than a 6. If it's a 100 amp service, or in this case a 125, and it's only being fed by 2-gauge, then as it says in table 250.66, it only has to be an 8. Okay? So an 8 could go to a ground rod if that's all that's necessary. Okay? Just remember that, again, it could be subject to physical damage, and of course then you'd have to protect it. Okay? So anyway, that's a whole different topic and I don't want to go down today. All right, so lastly, talking about the neutral loads. Again, I almost don't want to rehash this again, but the neutral calculation is exactly the method that you do for the standard. You just do all of the neutral loads, and you have to follow the standard method. So rather than belabor this and go through this again, I'm going to use that as a teaser to tell you that you have to go back and listen to the podcast on standard methods of load calculations for one-family dwellings. And in that podcast, I explain to you how to do the sizing of the neutral conductor, and it doesn't matter whether you're using the standard method or the optional method. You're going to size the neutral the exact same way. All right? All right. So that's how easy it is to do the optional method. Hopefully you got something out of it. You know, there's a big difference, right? The standard method took me an hour. The optional method took about 32 minutes or something like that. It is really, in real life, that's the difference. As long as you gather all those nameplates and everything, that it's much easier to do the optional method, and the code allows you to do the optional method. Just remember, if you're on an exam, they might want the standard method unless they allow you to use the optional method, and they will tell you that in the exam itself. Just be prepared. Know how to use them both. You shouldn't have any problems. But again, that's really simple concept. If you have any questions about this, by all means, email us at info@masterthenec.com. I'm more than happy to help you out. Okay? If you need consulting stuff, or you need somebody to tutor you for an exam, or you want to take one of our courses, trust me, if you think you get a lot out of our free videos and podcasts, imagine what you'd get out of our ultimate guide to the National Electrical Code. That is a real intensive 12-week course that we cover all of this type of stuff into such detail that it's almost blazoned into your mind and help you not only to pass a test, but down the road in your real everyday application. And that's where the rubber meets the road. Can you use it when you need it? And that's the key. All right. Anyway, hope you got something out of this, folks. Till next time, stay safe and God bless.
Every day, the future's getting closer. Every day, the future's looking bright. Every day is another beginning.